We are finally in a position to analyze Young's double slit experiment mathematically. Here I see Young's double slit, two slits in this little piece of, could be paper, could be metal, whatever. And my light source I've got on the left, a red light source. And as the light passes through the slit, it diffracts through each opening, and those two diffracted waves overlap and create this interference pattern ultimately on the screen at the end. And if I change the spacing of the slits, make them wider apart, I see my interference pattern becomes more frequent. And if I make the slits closer together, I get a less frequent interference pattern with a broader central maximum or a broader central bright spot. Similarly, there's a relationship with the actual width of the slits. You can see it becomes more or less defined as I make the slit width brighter, bigger, or smaller. And we're going to try and work out what this relationship is all about. So let's start by looking at a slightly different simulation and going back to what we talked about with the loudspeakers and the path length that each speaker had to travel. So in this simulation, we see we have a red light source, two open slits, and then the waves are interfering with each other and creating these diffraction and interference patterns on the far screen. Now, on the far right, you see this arrow. If the arrow is bright, that represents an antinode or constructive interference, and as I slide the arrow along, you see it gets dark to represent a node or destructive interference. Then it gets bright, dark, all the way along as predicted before. Furthermore, we see on the actual simulation the wavelengths. So the bottom slit, it shows the actual waves coming out of that slit graphically, and they have to travel a certain distance to reach my arrow. And similarly on the top, the waves have to travel a certain distance to reach my arrow. Now, as we've seen before, if the waves travel the same distance, and they're both the same wavelength, they originate from the same source, if they travel the same distance, they're always going to be in sync by the time they reach the screen. So it would make sense that right at the center, where we're equidistant from either slit, the top wave and the bottom wave will have traveled the same distance, and you can see on the far right that two crests coincide with each other, and that represents constructive interference. Now if I move it up slightly, where we get a dark spot, you see here that the bottom wave is now at a crest and the top wave is at a trough. And that's simply because the bottom wave has to travel a little bit further because it's got a bit harsher of an angle. So the bottom wave travels a little bit further, in fact a half a wavelength further than the top, and we know when they're a half a wavelength apart, the interference is destructive and we're at a node. And similarly, if I slide it up a little bit more, they get back in sync. You can see that we have two crests lined up, two troughs lined up. We're back to constructive interference and back to an antinode. So the bottom wave in this case has traveled one full wavelength further than the top. And if I keep going, there's 1.5 wavelengths further, we're at a node. 2 full wavelengths further, we're back at an antinode. So n times the number of wavelengths, where n represents the additional number of wavelengths that the wave has to travel. If n is a whole number, then you've got an antinode, and if n is a half, then you've got a node. Now let's take a second and have a look at what the equation will look like.